Well, hello students, how are you? How everything going?
Very good. Thank
Oh,
you.
good. Good.
Very good, very good. Nice to hear you. Because sometimes I ask and nobody answers. But it's good, very good. Thank you. Okay, let me do one thing, okay? I'm going to write down something that I need to do for you as well. Okay. Uh,
Hi, Professor. Can I ask you a question?
yes, please. I mean, sure. I mean, now all questions you want. Sure, sure. Sorry. I was writing what I need to do for you because I don't forget and I have now in my mind. But yes, please ask, ask.
Okay, so I saw in the model that we have homework until I think in 2 days or something like that.
No.
Deadline of
14th March. 14th March.
14th March. Okay, good. Okay, so
In 1 month.
in 1 month. Okay, good. And what type of exam we have?
No, there
It's
is no exam.
only homework?
Yes, only homework. Yes.
Okay, good. Thank you.
Yeah, another quick question, Professor. I haven't seen the recorded session from Monday
Yes, that's
on
correct.
Moodle.
Yes, that's correct. I mean, okay, 1 second, please. Just 1 second. I'm sorry, too busy. Do. 1 second, last thing. Okay, sorry for that. Okay, students, I'm so sorry, but I've been very busy. Okay, questions. Yeah, what I would like to start. If you allow me, I'm going to start answering. I think that all what I'm going to say right now, I'm going to answer your questions, okay? And then you, of course, can ask me questions whenever you want. Now, during the session, after the session, in another live, whenever you want, okay? Then let's start. Yes, one, I couldn't upload all the materials, nor the session, nor the recording because I was very busy the last days, okay? I'm very, very busy this week and it was impossible for me. Because of this, okay, I'm going to extend the deadline for the homework. Okay, the homework, moreover, for those people that was in the last meeting, I'm going to delete the deliverable too. And I will probably, I don't know if I will add another deliverable for this session or not. What I'm trying to say is the materials are going to be the same, but deliverable for second session will be deleted, only deliverable one, and today will be two deliverables for sure, maybe another deliverable. But the deliverables, probably I will change that. My guess is that I'm going to extend the extension, not only 14th March, probably will be later, okay, will be I don't know, later, or 2 weeks later, maybe because of these problems. And during the weekend, I'm going to upload everything, the recording, all. I will do everything during this weekend so you have all the information, as well as I will send a message to the forum with my final decision about the deliverables. But I think it will be 3 or 4 deliverables to deliver to me, and it will be in PDF or images or etc. But I will extend that so you have more than enough time till the end of March, probably Friday, 28th March. Okay, and there is not going to be any exam. I will clarify this in the message to the forum afterwards. So with that said, is there any further question, please? No, is now clear?
Yeah, thank you.
Awesome. Okay, is there any further question of the master or whatever that you would like to ask me, or something of your life or something? Anything? How you feel? Well, you too. I already asked how you feel. Sorry, very busy. And not, no time to stop, but now I'm happy to be here with you. So you told me good. Okay.
Yeah, just quick question. I might ask you something about next, so my company, we're kind of landing on quantum computing and all that stuff. So I might ask you some questions maybe in the forum, or maybe I'll send you uh, uh, an email or something
You.
like that.
Up to you. I mean,
Thank
if
you.
you consider that they are very private questions that is for your company, if you consider that they are very private questions and is for your company, just schedule, I mean, send me a meeting because you don't want anyone else to listen to it. Just send me an email, not a meeting, sorry. Just send me an email to my professional email that is, well, you have in the Moodle, that is the Accenture email, okay? And then
Yeah,
we will schedule a meeting. I will advise you as better as I can, okay?
perfect.
In case you think that your questions, of course, you always can decide whatever you want to do forever or for everything, okay? But what I'm saying is, in case you think the questions could be useful, could be in favor of of your workmates, of your mastermates, and you want to express that, of course, it's up to you. I would suggest that now is the moment to do it, or after the class, or but if you don't want to do it, I absolutely respect you. So yeah, that's up
Yeah,
to you. It's just that in case you think that the questions that you are going to do and you want to express that for the students that might be useful, now you can do them. Otherwise, no
perfect.
problem. And yeah, send me an email, and of course, I will be more than happy to do it.
Thank you very much.
No worry, pleasure. Any further suggestion, comment? No? Okay, let's go with the class. Who can tell me what is... Okay, we still need to close this. Who can tell me, I mean, what do we learn in the last class, on Monday's class? Did you learn something that's important? Because maybe you didn't. But did you learn something? Did you remember anything? No? No one wants to speak?
I wasn't there, sorry.
No, no problem, Osama. Anyone wants to speak? Three, two, one. Okay, no problem. I mean, I'm not going to force you to do it because I mean, when I was a student, I didn't want to be forced. I would appreciate the change, but you already. Okay. The main topic today, the class, is going to be more focused, more, I would say, practical applications, but please do not expect programming in this class, okay? Do not expect programming or being very practical. But today we're going to not see that much theory, but more practical applications. We will see what is the different quantum platforms, quantum hardware that we have. And where's not here? Okay, but the main reason, I mean, the main topics, the main concepts that I would like from you to take from Monday's class is basically two. The difference between analog quantum computing, and digital quantum computing. Can anyone tell me the difference between of them? Does anyone want who was in the previous class, Laura, Raul, or Daniel? In case you want. Otherwise, I will explain, no problem. No? Okay, no problem. The main difference is analog quantum computing is very similar to annealing quantum computing. And analog quantum computing cannot be programmed with the software. Okay? It's programmed in the hardware. As analog quantum computing is having a quantum state in a chip, putting the quantum state you want to have, and evolute simulated with the evolution operator during the time. This is analog quantum computing. It's programming directly in the hardware, let the quantum system evolve, and see what happens. Digital quantum computing is what we do in the practices class, that is programming with software. We have certain quantum gates, we program it, we send to the quantum computer executes it, and we get a result. This is digital quantum computing. analog quantum computing, programming in hardware, and let the quantum system evolve. Digital quantum computing, programming quantum gates and programming quantum gates and send to the quantum computer to execute these quantum gates. Of course, in both quantum computers, you are getting in both quantum computers, you are getting a result at the end. But this is the main difference. One, programming hardware and letting it evolve, evolution operator. Second, programming software and executing quantum gates in the hardware by the software programming. The other topic that you need to consider is the evolution from analog to digital, because since the very beginning, it was analog quantum computing. The was produced by Feynman. It was analog quantum computing to reproduce the world. But remember that Seth Lloyd suggested the trotterization decomposition, that is the deliverable one, made by theory. You will need to by handwriting or latex. So the trotterization decomposition, that what it allows is decompose in more elementary gates and be able to program in digital computing, meaning that the last topic that I would like to remember yourself is, thanks to the trotterization decomposition, one can decompose the evolution operator or any operator into elementary quantum gates and be able to program it in digital computing, meaning that the transition from analog computing to digital computing is thanks to the scientific paper of Seth Lloyd, and be able to decompose in elementary quantum gates. And this is very important for in terms of history and theory of what quantum computing is in terms of programming. This is very important. The totalization part was super important. When I started working on quantum computing 8 years ago, at the very beginning of my career, there wasn't any kind of function like today Qiskit. In fact, we were asking a lot, the programmers, we were asking a lot from this function, and Qiskit provided us. But there was no function to decompose the operators and the elementary gates. And what did we do? What we did is that we really understood, we really analyzed the totalization decomposition, and we implemented by ourselves. And through, for example, in my case was a Python programming, or for other people, Mathematica or the fact, with a Python programming, we were able to get from the operator the elementary quantum gates. That's why it's so important. So from the previous class, to really sum up, is one, analog quantum computing. Second, digital quantum computing. Third, trotterization decomposition. Okay? As of now, is there any question?
Yes, so I just want to ask you, Professor, what you mean directly programming in the hardware? So we manipulate the hardware to get results directly, or how we can do that exactly?
When I mean programming the hardware, is that yes and no. Okay? You were saying that you are directly manipulating the quantum state. No, you cannot do that. You will never be able to do that, because if you can directly and perfectly manipulate the quantum state, it is not the quantum state itself. Why? Because you are seeing it, you are really controlling it, and you are being classical. So you cannot do that.
So
But
observation,
yes,
like observations when you get measurements. That's
correct.
why you're
Yeah,
okay.
but if you want to control everything, like if you make from an observation, if you are performing, it's because you are controlling all the system perfectly, like do this, or something like that. No, what is being done is you let the quantum system be there. And what you do is not observation. What you do is perturbations. You create electromagnetic fields, but from the hardware perspective, it's the same like digital. In digital, you are doing the same, but in digital, it's based on quantum elementary gates. Here, what you do in the programming, when I mean analog programming in the hardware, is that you have a chip, and then you put you have a chip with a quantum system in all quantum states. I'm going to show you an image now and you will understand. You put the system in quantum states and then you apply the evolution operator, okay, that the evolution operator are electromagnetic waves. So you apply the evolution operator and it changes from one state to another. But you are not applying elementary quantum gates. I mean, it's an operator, the evolution operator is not the specific elementary quantum gate.
Okay, understand.
Does it make sense?
Yeah, okay,
I always think that an image is better than a thousand of words.
okay.
Oh, this is what happens and is very similar to adiabatic quantum computing that I realize that you are studying now, or to the analytic quantum hardware. You is from state B to state 1, okay? You prepare the quantum system into all the different states in the same superposition and everything, okay? And what you do is that you let the system evolve and you finally get the final state that is your state that you wanted. You get the final state, you know? In digital quantum computing, this is not happening. In digital quantum computing, you have all the states in the same manner, and then you need to apply the Hadamard gates to apply the electromagnetic fields that will convert this into this. And then you need to apply another elementary gates, 1, 2, 3, 4, that will apply electromagnetic fields, and this will change the quantum system. But in analog quantum computing, you are just putting everything in this state, in a superposition states of all the states, and then you finally get, by applying the evolution operator, the final state you want. Does it make sense? Is it clear, Sama? Now?
Yeah, clear. Yeah, thank you.
Okay, no, please share. I mean, I'm here for that and to help. Thank you very much to your question, Osama. Is there any further question? No? Okay. What are we going to see today? As I mentioned, today is a much more. Can you hear me properly? Yes. Maybe I
Yes.
could.
Yes.
I'm speaking too loud. Maybe I'm going to put my microphone. Because I'm speaking very loud and sure that you hear me, but it's not good. I'm going to, and then I can speak not that loud. Okay, students, can you please, guys, can you talk to me so I can hear you? Can you hear me now?
Yeah, we can.
Yes.
Yes, awesome. Perfect. Then I can speak more calm and not be shouted and loud. Okay, perfect. As I mentioned, last class was much more theory because I wanted you to understand the difference between analog quantum computing and digital quantum computing. And as I mentioned, the totalization decomposition, the totalization steps. Today is going to be more a practical session, but more practical in terms of experimental results, etc. And in fact, I think one of the deliverables that I will add here is that you will perform a research or of what is the most advanced practical implementation of quantum simulation. Okay, this is the only deliverable that I think I will add based on the one I deleted in the previous session. Still need to confirm, but it will be very probably that will be that. Based the first one of last PPT, the two of today, and then another one of research to analyze a scientific paper and you comment it. Okay, but there's just basically because thanks to that you will be aware of what is the current state of art of quantum simulation and digital quantum computing. So let's go with this. Okay, now very simply. I mean, we have two types as we saw. We have two types of quantum models. On the one hand, we have the fermionic model. On the other hand, we have the boson model. Both could be used for quantum computing. Both. It could be fine. I mean, it wouldn't be a problem. But in order to get for digital computing, because in analog you can use both, but in order to get for digital computing, only the fermionic
Only a fermionic model is used in quantum computing for digital computing because the main reason is because in fermionic computing you have a you have a much more controllable of the energies, meaning of the ground state energy and the excited states of the different particles. Because in every energy step, just as we are using electrons in digital computing, most of people, well, neutral atoms as well, but the decretization of the energy and the restrictions of how many particles can be in every energy state, it allows you to really compute with these systems. That's why in digital computing we only have fermionic simulations. But here we have, on the left side part, we have the boson simulation. And in the right side, the B is for fermionic simulation, okay? This is bosons, right? Because I always confuse that. Let me check. Yes, correct. I mean, I was sorry, but I always confuse that because I always learn first the annihilation and creation systems like this. I always think that this is fermionic and this is boson, but no, it's the opposite always. So I'm mixing. Sorry for that. But yes, I mean, this is bosons and this is fermionic, and both of them, even the difference between boson and fermionic, boson is that a lot of particles can be in the same energy state, and in that's why it's shown like this. A lot of particles can be in the same state, while in fermionic, just few particles, well, not few, a specific number of particles can be in the same state is shown like this. Okay, this is the anti-commutation relations in bosons and fermionics. Both in both places they need to be considered and fulfilled. Okay, now I need to understand one question. I need to ask you one question, sorry. um, you have a preliminary subjects where you have quantum mechanics, right?
Yes, so like
Yeah.
not directly quantum mechanics, but it was like introductions quantum computing or something like that.
Okay, I mean, okay, and then I'm going to make the specific question now. Did you play with the Dirac notation? And did you, from a certain operator, obtains the different levels of energy, the different energy levels, and the uh, degeneration of these energy levels? Do you know how to do that?
You mean energy levels of electrons,
That's the
or
I mean, this is what I want to know. I mean, in general.
so I know about Dirac equations, and that describes, I think, the quantum states or something like that. And in this Dirac equation, we can find also the energy. We can calculate or we can find the energy state of the particles.
Okay, if I put you an operator of 5 per 5, what does it mean? Do you know the answer? Or
Uh,
you, okay, no, I'm going to make a more simple question. Do you know the more simple question? Did you ever calculate? I mean, did you ever work with another quantum system that is not a qubit, that is a qutrit, or it has more than just two energy levels?
uh, so I know about quantum annealer, for example, but I just only worked with qubits until now.
So the answer
But
is no. Okay,
yes,
it's not a problem, Osama. I mean, it's not a problem. Yes or no? Not a problem. It's just I need to understand that. That
it's no. So as I said, I just worked with qubits. So
so you just work in qubits, this master, right? For the rest is the same. I mean, if I told you here there are instead of two just energy levels is 0, 1, 2, 3, 4, 5. Did you ever see that or work with this
Yes, we have worked with higher energy levels.
with 2, 3, 4 and as well, Laura?
Yes, we
I
have.
mean, probably you know based on your previous experience, but in the master as well.
Yes, I think we have already played with the tensor products to create higher energy levels. So Yes.
Understood.
So yes, we do have this 0, 1, 2, 3, 4. So it's like state vectors, and I don't know how we can calculate from that energy states or something like that.
Okay, thank you, Osama. Basically, I mean, to calculate the energy states is with the Schrodinger equation. I mean, operator Dirac. I mean, no. I mean, to calculate energy states, it's very with the Schrodinger equation always. And I know this is not correct, sorry. This is the second part. Operator, edge, or you can put U, right? Is equal to energy N, where N can be, it was a 0, 1, 2, can be even 0, 0 to N, right? It was N, the N, the quantum number N. But yes, I mean, what I wanted to know is, I mean, I was asking this question, and thank you very much, Osama, Laura, to answer the question. I mean, I just wanted to ask you this question because I just wanted to know if you just work with qubits or you know more. And this is the fact. I mean, in quantum computing, we're always working with qubits, so there are just two energy levels because it's much more simple for digital quantum computing and analog computing to detect the ground state energy and the excited state energy. Okay, it's much more simple. But in the very, very long future, there will be quantum computers with qubits or four states levels. The problem is that, I mean, if today, nowadays, we cannot control a quantum computer with two, two quantum states, that is 0, 1 from qubits, how are we going to control a quantum system with 3, 4, or n quantum states? That's the reason. But I just wanted to let you know that now we are in the simplest case, okay? Even bosons, well, it's all fermions, but even bosons, we are in the simplest quantum state. But now we are encoded every single because we are in the simplest, I might say, in the simplest way. But there are other ways, okay? As well, in theory, you can 0, 1, 2, 3, and higher excited states and compute that with an operator, etc. In quantum computing in the future will be the same because we have now an exponential level to 2 to the n, but probably in 100 years or 150 years or even earlier. I don't know, honestly. I mean, if it's difficult to predict when quantum computing is going to give advantage in business, imagine to say another type of quantum computing. So, but in future, in 150 years or whatever, you will get results for three different systems because it will have much more advantage. It's
Yeah.
just the reason of my questions. Yes,
So
Osama, please.
yeah, so that means we can put a quantum system so in superposition of three states or more than three states.
Yes, of course.
So it's not
No,
like
no quantum, not current quantum computers.
yeah, not current. I mean in the future. So we can
Another
put
type of quantum computer.
yes, we can put superposition of more than two states in just one qubit.
It will not be a qubit. It will be a qutrit.
Occurrence. Okay. Okay. So when we apply Hadamard gate, we will not get only 0 and 1 with the amplitude. Otherwise, we will get 0, 1, and 2 with an amplitude. So
Correct.
1 over square, 3 squared. Yeah.
Correct. Well,
Okay.
qubits grows 2 to the n, and qutrits will grow 3 to the n. That's what it will be an exponential advantage over here.
Mhm. Okay. Great. Great. Great to hear something like that.
Qutrit or, I don't know, 5. I mean, all you want. L to the n.
So it will be really powerful, so more than the current quantum computer.
Yes. Correct. Okay, it's clear for the rest? Yes, I mean, it just was giving you a more broader overview of what it means. And okay, well, then we have bosons that it relates the bosons. That's why I'm always confusing because we always use electrons, but when I study quantum mechanics, I learned creation annihilation operator with the commutation relations. That's why I'm confusing. But the bosons obey the commutation relations. What does it mean? That two particles can be in the same state, while the fermionic obeys the uncommutation relation. That it means that the same particle cannot be in the same energy state. That's the reason, okay? I mean, bosons are commutation relations. It means that the same particle can be in the same energy level, while fermions means the uncommutation relations. That means that the same particle cannot be in the same energy level, okay? Then let's continue. Okay. Basically here is enforcing what I said. I mean, okay, it's just today nowadays we are getting qubits, okay, and more we are getting qubits because we are controlling electrons. The reason for that is twofold. On the one hand, we are getting qubits because it's a very easy way for quantum hardware developers to distinguish between the ground state energy and the higher state energy, the excited state, okay? And if you want higher state, you need to do a form with the qubit, that it has just two ones, okay? So the basic unit is a spin, is this fermionic of minus one half or plus one half, okay? But it is not different, but basically the main reason is what I said. Uh, for hardware hardware developers to make that. The second reason is more from theory perspective, that it belongs, it is intrinsically correlated, it's intrinsically adapted to the first reason, is that the theory says, I mean, the harmonic oscillator for three different states is well studied, but the most well studied harmonic oscillator is from the hydrogen oscillator, the simplest molecule, and this is the most well-studied oscillator, meaning that, as I mentioned, for quantum developers to create the difference between ground state energy and first excited state, it's simple for developing. But moreover, we also understand perfectly, well, not perfectly, sorry, but we understand at most the simplest state. And the simplest state is an harmonic oscillator of two different levels. That's the reason of why now today quantum computers are working with qubits. Okay, not other. What else? What can I do? What is said here? I mean, basically, I'm trying to control, or maybe in just one qubit, one single qubit gate is simple. But the problem comes with with two qubit gates, and I don't say three qubit gates. In fact, in current and future, in the following 100 years, current and future digital quantum computers. Okay, because analog, remember that you just put the quantum state and let it evolve. Now we are speaking mostly of digital quantum computers, but you'll just let it evolve applying the evolution operator. But digital quantum computers, even if you compute like in the previous class, Grover algorithm, when you have a 2, 3, 4, 5, 6 quantum gate, you decompose that into elementary quantum gates that are one qubit gates, maybe two or three, the identity SX and identity SX and another one, and then just one two qubit gate, that is the C naught usually, or another type or another specific gate. But all the quantum gates in digital quantum computing that are more than two is 3, 4, 5 quantum gate. That is, it means that is related to all the gates. It is decomposed in one single quantum gate, one qubit quantum gate and two qubits quantum gate, always. And the main nowadays for digital quantum computing to progress, to advance, the main aim is to get the main advantage is to get decreasing a lot the error in the 2-qubit quantum gates, more than the one, because the one is simpler and easier. As I mentioned, the bosons are following the commutation relations, okay, and they are most used in an analog way, okay. In the Bose-Einstein, they can be, I mean, the Bose-Einstein condensate that are bosons, they use in analog quantum computing, okay, is where most of the quantum simulators are used. They use bosons. That's the reason why we are looking into it. While fermionic are using basically in digital computers. Okay, what is the reason? What's the difference? In bosons, you can, as you just need to let the system evolve, you don't care about where the qubits are in what system state or not, and you can have more qubits. Okay, so you have a lot of qubits, bosons, and then you can just let them evolve by the evolution operator that just giving in time, and then it evolves and you get finally the result. In digital quantum computing, the reason why we are getting fermions is because you can really distinguish between the ground state and the excited state, and that's why you can really apply quantum elementary gates like the single qubit gate and the 2-qubit gate, and you can get better, not better performance. You can control, it's not control, okay, because I don't want to say controlling, but it's like you can really apply perturb electromagnetic waves to get a result, because you want every specific qubit to do something by perturbing it, okay. Sorry, because maybe misunderstood. I'm going to sum up now. Is bosons are used for analog quantum computers because you don't need to specify to each qubit what it needs to do. You just have a lot of qubits, maybe in the same energy level, and let it evolve. While in digital quantum computer, we use fermions because as the same particle cannot be in the same energy level, you just have fermions and use them applying electromagnetic waves, tell every qubit what it needs to do. So it's easier. Okay. Then we are going to see the Jordan-Wigner or Breivik-ITAF transformations. They are very important, almost for quantum chemistry. Okay, because when you get an operator, I mean, for quantum algorithms like Grover, etc., you don't care about it, okay? But if you really would like to get a operator evolving in a quantum computer, you need to apply the Jordan-Wigner or Breivik-ITAF, one of those transformations to transform the Hamiltonian, the operator, into a language of the quantum computer. I mean, we have an operator, we have a Hamiltonian, okay? That we want to evolve or to do whatever we want. So if we want to insert this in a digital quantum computer, we need to apply the Jordan-Wigner transformation or the Breivik-ITAF transformation, one of these two. I think there is another one, but I don't remember now. But you need to apply it to translate this Hamiltonian in an expression that you can insert in the quantum computer. If you try to the Hamiltonian with the Ising parts, etc., if you want to translate into the quantum computer, it is impossible. It's not the same language. That's why you need to use these transformations. Where it is, okay, till now we go for more the practical applications. Till now of the simulated models, is there any question as of now, please? No? Awesome. Then, what are the different areas? We already saw that in the previous class, okay? But basically, I'm here highlighting the more academia sizes, okay? The first one is condensed matter systems. Honestly, as of now, I don't remember any specific other application rather than condensed matter system was used to create graphene. Okay, I mean, the analysis of the condensed matter was very useful. Of the Bose, condensed matter is Bose-Einstein, I think. Sorry for my theory, long time at the university, but I think so. Condensed matter is Bose-Einstein, and it was very useful to create graphene. Okay, in quantum chemistry, the quantum simulators, as we mentioned last class, drug discovery is basically the main one. Okay, in fact, where we think, and I think as well, that is going to be the first advances, a real quantum adventure in industry or wherever place of that will be with analog quantum computing for quantum chemistry. Maybe to reduce the carbon footprint of our atmosphere, uh, designing designing an spray that can can neutralize the carbon dioxide, for example. So I really think that. And finally, in high energy physics, okay, this is used for understanding the laws of physics in terms of the of black holes, how the universe is working, how the planets are interacting each other, etc. Okay, then let's see that in a more deeper way. Okay, as I mentioned, the content matter is more for design novel materials, but the main fact here is to really understand the different phases of matter, the quantum phases of matter. That's why I said that I am aware that the graphene was very useful, the understanding of the condensed matter, because graphene is another state of carbon, is another composition, and by analyzing it, it was useful. But basically, sorry. But yes, I mean, if you want to get a knowledge of quantum here systems, it's basically that they are using quantum system with fermionic models. Okay, we have different models here, like can be that characterizes different states of matters. That can be the Kondo model, the Hubbard model, or the Frulich model. And then by applying these different interactions, you can have, by applying these different interactions, you can convert from a quantum system to a digital operator. The first, as I mentioned, if you really want to translate one of these models, you see, in condensed matter systems, if you want to translate this Hamiltonian of a certain quantum phase system, these are different quantum phase systems, okay? States of matter, sorry, different quantum states of matter. So if we want to translate that, insert that into a quantum simulation for a digital computer, what you need to perform first is a Jordan-Wigner equation, Jordan-Wigner transformation. So you change this language that is not useful for the quantum computer to the language of a quantum computer. Okay, that is changing from annihilation and creation operators to the matrices, the Pauli matrices. Then you apply the Trotter expansion, the Trotterization decomposition to be able to decompose this Hamiltonian in a certain grade and insert into a quantum computer. This Trotter expansion is used very similar than, for example, when you apply I don't know, I don't remember now the name, but the trigonometry expansion that you have a sinus of x, but then to calculate limits, for example, you were putting like sinus is 1 plus x or minus x to the 3 divided by 3, right? I mean, this is the same idea. You do a Trotter expansion and you get just the few first numbers, and this is the ones that you insert into the quantum computer. And finally, you are able to efficiently implement the Hamiltonian with the different spin operators into the digital quantum computer of qubits. Quantum chemistry is exactly the same. In fact, here in quantum chemistry is where the VQE is used. And this you will see that you will have a specific chapter in the following subject of A11 of programming with quantum computers where you will see exactly this. I mean, when I see exactly this is, well, quantum chemistry is for designing new medicines, etc., for understanding the properties of a new material, etc. Okay? So, how does it work? You will see much more deeply, okay? But I'm going to explain you. You will have a molecule, for example, the H2 molecule, you will execute that. You have the H2 molecule, and this H2 molecule you will decompose by a Jordan-Wigner. I mean, you have an H2 molecule, and first of all, you will use the Born-Oppenheimer approximation. It means that you will reproduce the Hamiltonian with the von Oppenheimer approximation. There are other approximations like which was called, I don't remember now, sorry, but there are other approximations, okay? Then you will use a transformation, Jordan, Wigner, or baby K8F. You will do the deliverable about that. I will explain you afterwards, but you do a transformation and you convert this Hamiltonian that has annihilation and creation operators such a way, okay, no, such a way like here that is feasible to compute in the quantum computer. And then you have that, you will include that in the VQ algorithm. The VQ algorithm is the variational quantum eigensolver that can perform operations to guess the ground time state energy of a certain operator, of a certain Hamiltonian, of a certain molecule. So here will be very important, and you will understand this in a very step-by-step detail. But in quantum chemistry as well, here I think is going to be one of the first quantum advantage, because in digital quantum computing you can use the VQE, but in analog quantum computing you can directly put in the quantum system the molecule and let it evolve to see what happens for certain conditions. And finally, in high energy physics, that they are basically studied for quantum field theories, to understand the universe, to understand the universe, to understand how the galaxies and the planets interact each other, etc. Okay? Then there are, of course, other areas of applications, but as of now, in digital quantum computing, other areas of applications is, for example, optimization problems, machine learning. But in analog quantum computing, these are the main areas: quantum chemistry, condensed matter, and high energy physics, because are the areas that, I mean, it's more academia. Analog quantum computing is not that much in business, it's more academia. And that's why they are focusing in these areas, because it's more academia related. Then, what are we going to see now? I'm going to pass this very quickly, okay? Because I want to show you some aspects, but we will then go for a comparison between different quantum platforms, okay? Devices for quantum simulations. Here you have some, like the cold atoms. It was one of the first that was used. On the one side, you have the cold atoms. What is, I would say it was the first quantum computer, first quantum simulation to simulate the transition of the superfluid mode insulator. It was the first scientific paper where a quantum simulation was demonstrated. Then another quantum simulations are done in trapped ions like IonQ, or superconducting circuits like IBM and other ones that we are going to see now. And finally, we have another quantum simulation, quantum computer, that is very well known. That is quantum photonics. That is the one for Quantinum now. Before it was called Xanadu, and before I don't remember now the name, but it's for Quantinum. In fact, I think now they release a paper saying that is, I mean, that they claim something. I don't remember now, but they claim something in quantum photonics. Then I just want to see that very quickly, because you can have time to read that. Okay, maybe we can explain this in more detail, and then we go to the comparison of all the different quantum platforms that we have available in the market. One very important notice that I didn't say, and is very important, is this last center over here. We still need a lot of, okay, we still need a lot of improvements, a lot of advantages to really get a fully scalable and fault-tolerant quantum computer, meaning a universal quantum computer, an universal quantum simulator. Okay? But of course, I don't want to disappoint you. I don't want to make you sad. Why? Because you could say, why am I studying this master if a really fault-tolerant or quantum computer still needs to take a decade or more than a decade? Because I would say it's true. Well, because of basically two reasons. One, my really guess of a real quantum advantage, that for me quantum advantage means a process that completely replaces a classical process in production, will be with in quantum chemistry, a quantum simulation. But a quantum advantage in the sense of having some speed up by the near hybrid architecture of combining the best of both worlds of classical and quantum computing, this will be achieved in the following 5 years, in my opinion. When? I don't know. It will be the smarter who will get it, but it will be achieved in the following 5 years. That's why this is the first reason, the following 5 years. That's why you need to study. And the second reason is because the talent is very scarce. And as I think you can see in this master, quantum computing is not the same than quantum computing is not the same than classical computing. And it means a revolution of the mindset. It means a revolution of doing everything. So it's a revolution. It's not I mean, everybody can learn and everybody can upskill, but it takes much more time that, for example, someone that understands of artificial intelligence to understand of Gen AI. This is quite different. This is another way of thinking. This is another mindset. So it's important to start now. So you are going to be prepared when this happens, because people, when this happens, start studying, there will be outstanding. Right? It's outstanding, correct? Right? They will be old-fashioned compared with the people that, as you already started studying. Sorry, yes,
Outdated.
outdated. Thank you very much. Thank you very, very much. I'm quite tired, but thank you very much. Okay, so let's continue. Cold neutral atoms. Cold neutral atoms, I would say, is the same in the past. Is the first quantum simulation, and nowadays is more used for neutral atoms that we will see. That it comes. I don't remember the company, but we will see it now. Okay. So cold neutral atoms are very, I would say, cold neutral atoms are. There was the first quantum simulation. Is very, very. It is very important to understand from the history and to understand that they are important because they were the first time, but they are not good at scaling or something like that. So it was good to understand that the first scientific paper comes from it, but it won't have anything else. Trapped ions and superconducting qubits, they are very important. They are the ones nowadays that seems that they are going to provide this scalable and fault-tolerant quantum computers for the future. IonQ already provided an architecture to scale all the quantum computers up, and IBM and others, startups, etc., also claim these different architectures for superconducting circuits for the ones that are, to get that. They have drawbacks and advantages and disadvantages. Okay, but they are the most used nowadays. Okay, you have this information here. I prefer to say all of this in the following document that we are going to see. Okay, but these are mainly used with fermions and in digital quantum computing. Okay, just very quickly, trap ions has the ability that all the qubits of the quantum computer are correlated. This is an advantage. The disadvantage is that scale that up is very, very difficult. While superconducting qubits is the opposite. They do not have all the qubits correlated, but scaling up it seems much easier. For example, we will see that in a few moments. Okay, and both of them works with electromagnetic wave. Okay, so this is and quantum photonics, the lattice. This works a bit different, okay? Because it is also used for, it can be used for quantum simulation and digital computing, okay? Quantum photonics, but is mainly used for digital computing from Quantinom, okay? They released the lattice quantum computer a few months ago or a few weeks ago even. And here says that it's used for quantum machine learning is true. I mean, Penny Lane, this is what we will use as well in the future subject of quantum machine learning. Penny Lane is my favorite programming language for quantum programming language for quantum machine learning, and it uses photonics view. And the difference between the others and quantum photonics is while IonQ, while trap ions, because cold atoms we don't use it. It's now neutral atoms. But while trapped ions are superconducting qubits is the digital from the programming from IBM, they are like discrete energies, etc., entanglement. Quantum photonics, they are using like waves. So every qubit is treated as a wave, not as a two discrete system. Trapped ions are superconducting as treating qubits in the digital programming like discrete energy levels, while quantum photonics are treating qubits as a continuous discretization of the energy, is not discretization, as a continuous energy level. So instead of having, for example, it's treated the same because at the end you do the same. But the fact is that while in ionic and superconductings you have two different ones, like in in quantum photonics is a gate. When you program quantum gates, etc., you are considering the qubits as waves, not two discrete levels. Okay, these are some of the scientific papers that I will put you. Okay, and I want you to review because as I mentioned, there will be a deliverable around that, probably to do research of the latest advances of quantum simulations. But this is some papers from the history that you can take a look. They are quite old, like you can see, 2010, 2002, the first one. But we can comment them, but honestly, I would prefer from you, I put you this information so you have it, but I prefer from you that you do this research. Okay, this is just advancement in the past because now there is much more advancements that you can take a look. This is just for information. Okay, let's see the deliverable and then we will see. Okay, here I just suggest you a way of, here. Okay, then you have here some history of simulations that we already discussed, how it was evolving of scalable for quantum molecular energies, quantum simulations, etc. But this is a bit outdated. Okay, but I thought it was interesting. And here, as I mentioned, this is an open question if you want to answer, but I will answer myself, and then maybe we can go to the difference between the different hardwares. And is that no one know when the quantum advantage will come, even if Google claimed it some months ago. No one knows when the quantum advantage will come and how it will come. No one knows. My guess is that the first real quantum advantage will come from a quantum simulation, an analog quantum computer, okay, for quantum chemistry. But in industry, a real quantum advantage, meaning that some hybrid architecture or some process is completely replacing production from a quantum process, I think it will come from analog quantum computing as well, but more from annealing quantum computing, that is digital. Digital quantum computing, but applying the mindset of analog quantum computing. So this is my idea, and it will be in the following 5 years, honestly. But yes, but this is an open question. I don't know if anyone want comment here, but no one's know anything. Okay, so the future is still very open. I really think that this career of quantum has a lot of power and energy for the future. Not today, not much today, because today is very difficult to find a job in quantum, etc. If you don't do AI, honestly, because when ChatGPT releases its announcement, all the budget went to there. My main enemy is Gen AI every time, but now is no one knows. But my guess, if I should say something, is that in the following 5 years we will have advancements, progress, and a full scalable and universal quantum computer will be in a decade or more. But no one knows what is going to win to each other or what is going to be more reliable. Finally, the the homework. Homework task one for me is very important. Understand the different transformations that you have for quantum computers. Okay, understand the different transformations that you have for quantum computers. And then once you understand, make the advantages and disadvantages of them. I will rephrase a bit the homework, but the main thing is that you analyze, understand the transformations, and they put advantages and disadvantages. And homework task 2, I will change cold atoms here, that's what I'm saying, but I will tell you to get 2 different quantum platforms and analyze their advantages and disadvantages as well. And finally, there will be from this class a third homework based on the story of the different scientific papers. Okay, but my homework will be this is a research of the latest or the most latest scientific paper. It does not mean that if you analyze instead the latest, the second latest, or the third latest advancement, is that you're going to fail. No. I mean, the goal is not that. The goal is that you do a research, you get one of the latter scientific papers of quantum simulations, and you read it and then describe it, why it's important, and what is the more advancements to the previous one. Okay, I will explain more detail and I will rephrase everything in more detail and put you very clearly to all of you by this weekend. Okay, then let's see now what I wanted to see. I will upload everything into Moodle, no worries. Okay, what do we have here? What we do have here is a comparison of the different providers that are available in the market. Okay? And you have here some references, etc. The first one that we have, IBM, superconducting qubits. IBM published that the latest is the most biggest qubit that they have is 1121. For me, this is physical qubits. If we transform into, if we transform, if we transform into logical qubits and they have correlated, etc., I think might be not more than 50 or 60. That is a lot, but it's 60 qubits, but the error window is very short because IBM, their strategy is increasing in the number of qubits, and once they have a lot, 5,000 or 10,000, I think that they want, or 100,000, they will work on the errors and decrease the window, the execution window. Okay, and the latest computer is the IBM Condor. Advantage is scalability, and there is a quantum chip that is easier to control. Easier when I mean easier, okay? What are the disadvantages? Very low temperature. You need a full room to decrease the temperature of the quantum chip to be able to control it, to have it at least in 0 Kelvin, that is around 0.17 Kelvin. And then the physical qubits are not logical to the equal qubits, meaning that this is one, but for us, that we are developers, what we really want is logical qubits, meaning that qubits that are correlated to the other qubits and we can control them. EQM, the same than IBM. Superconducting qubits is the same type of computers. The problem is that the architecture says the latest information is from 54 to 150. DWEF is supercomputing qubits, but these are annealing. And the latest that they have is 5760. For me, it's very weird because 5760 is a quantum computer that they released like probably 8 years ago or something like that. So I really think that they are going to make a big announcement this year with a quantum computer of 100 or 500 qubits or something like that. This is what I think. Advantage of this type of quantum computer with this type of hardware paradigm, that this is analog quantum computing, is very similar, that is much more mature. Here you have 5,700 physical qubits, but the logical qubits are much bigger, like 1,000. It was not 1,000, it was 500 logical qubits or something like that. It's true that the error window was not enough for even for this 500, but it's good enough. And finally, the disadvantages is that you can only solve with annealing model only solve of optimization problems. That's the reason why this is much mature. It is much mature because it can only implement one specific reason, one specific problem, optimization problem, not quantum machine learning, or for example, the Grover algorithm or the HHL algorithm or whatever. Okay? Then Kilimanjaro from Barcelona, superconducting qubits. There is not much information about the number of qubits, but they are really claiming that they have a very, very, very good gate qubit quality. Okay? What's the problem as well? That is annealing and they only solve optimization problems. But they have a very good, very, very good quality in the qubits. So they are very, very focused. Instead of increasing the number of qubits, they are very focused on error correction in the hardware. Okay? That's why they are doing annealing. Then quantum circuits, they are not giving much information. Okay? Yes?
But,
Anyone wants to ask something?
yes. So in the wave, they have quantum annealer, and I don't know if this superconducting qubits need low temperature also or not.
Yes, they do need. Yes.
Okay, so it's also disadvantages, I mean. But
Yes. Yes. I mean, here, this is complete, but not that much because I want you to do the deliverable as well.
okay, good. Okay, but they are also, I know that only for optimization problems, so they are like, I don't know, trouble state management or something like that. And what is the difference between the superconducting qubits in IBM and D-Wave? It's
Bec-
quantum annealer by they also have the same hardware.
no, they have the same construction. I mean, they use the same hardware pieces to build two different quantum computers. One is digital quantum computer gate model, and another is annealing model that is analog quantum computing.
Ah,
One is used to simulate the evolution operator, and the other is quantum elementary gates.
okay, good. Thank you.
Does it make sense, Osama? Is it
Yeah,
clear?
yeah, it's clear.
Thank you for the questions, Osama. Thank you.
No problem.
Perfect. Then quantum circuits, okay. Fujitsu, they are building a gate model quantum computer for the future, but they didn't say anything. But as of now, what they have is a quantum inspired hardware. What does it mean? A quantum inspired hardware is a classical hardware that is using GPUs or FPGAs, okay? GPUs, FPGAs, or whatever of the visual graphic target. Oh, visual graphic cards that we have, all what is inside to create combinatorial problems, meaning that to simulate the same like an annealing model, an analog computer, meaning that it's very powerful, but it's used only for combinatorial problems, meaning that optimization problems. Okay. The main advantage of Fujitsu is that they are all logical qubits. Okay. And as of now, Fujitsu and Toshiba has the most advanced quantum inspired computer in the market. If you want to really put something in production, you need to use a quantum inspired hardware. Rigetti, superconducting qubit like IBM. I think they have a new one here, but their main advantage is that they are really relying like Kilimanjaro for analog, but they are really relying for digital computing for error correction, meaning that they are really trying to get 2 qubit gates at its maximum 2 qubit gates as its maximum performance. Then we have trapped ions, okay, that is IonQ, where we have gate models. What is the good thing here, as I mentioned previously? Their scalability is very difficult, though IonQ promoted an architecture to scale it up, and they are working on that. And I think they increased, but they didn't announce it yet. But the good things of in trap ions in IonQ is that all the qubits are logical qubits, meaning that if they are claiming 32 logical qubits, is because the 32 qubits in the trapped ion are all fully correlated. Neutral atom. This is very interesting because neutral atom is a quantum computer that can work as an analog computer is very similar to the Coles atom, to the very initial one. But now they are using neutral because it's more efficient it's in qubit temperature. Okay, but neutral atoms is it can be used as an analog computer letting the operator evolution time evolve, or as a digital quantum computer. They can be in gate model or annealing. They have a lot of qubits, 256, and its main disadvantage is that the 2-qubit gate operations are very, very difficult. And the electronics to control the hardware are very, very difficult as well. But as hardware, they are very good. That's why Pascal last week got a lot of funding from friends and from a lot of investors for the following years. I think it was like 10 million euros or something like that. A lot of money. Because Pascal is also neutral atom and they got 100 qubit. Finally, Quantinum is allo trap ion, and they have a then Quantinum is trap ion, then is Xanadu photonics. Sorry, because I was saying all time Quantinum is what's photonics, then I mixed my mind. Sorry for that. Quantinum is trap ions. Okay, is a gate model quantum computer, and the same that IonQ scalability is very difficult, but they claim now that they have very good errors, etc. But all qubits are logical qubits. And finally, also quantum circuits is also supercomputing, but they are really keen to improve the hardware by error correction. Okay? And with that said, students, this is all what I wanted to show you for today for this class. As I mentioned, I will put everything in the Moodle by this weekend because this week I'm very busy. Sorry for that, but I will put everything. I will specify anything. And of course, anything you want, just let me know and you can email me and we will quickly have a mentoring session or whatever you need. Okay? Before finishing, is there any further question you would like to ask? No? Okay. Then thank you very much. I'm going to stop recording.